Welcome to section 4.3 on bases. So last time we talked about null A and col A, and today our goal is to find a basis for null A and col A. So first we have to figure out what a basis is, and before we can do that we need to revisit the definition of linear independence. Now I've got that definition in this box here, and this is the same definition we learned back in section 1.7. The only thing that's changed in this definition is now it's a more general definition for any set of vectors in a vector space V. They don't have to be vectors in Rn. And so all of the results we learned back from Rn still carry over. So these are all from section 1.7, so I'm not going to read through those. And so let's look at first some examples of linearly dependent sets and then some examples of linearly independent sets where the vectors are not from Rn, so we can get a feel for what this means. So in P2, which is the set of polynomials of degree less than or equal to 2, I've got 3 polynomials here, and my claim is that those are linearly dependent polynomials. Write down a dependence relation. All right, well, we can see just by inspection that P2 is negative P1 minus 2P3. So a dependence relation would be P1 plus P2 plus 2P3 is 0. So a dependence relation is an equation of that form where not all the coefficients are 0. All right, in M22, which is a set of 2 by 2 matrices, we've got 2 vectors here. Those are also dependent vectors. If I call this V and this W, we can see, again, by inspection, that W is twice V. Well, we know from Rn that if we have a set of exactly 2 vectors and one is a multiple of the other, that's a linearly dependent set. And if you wanted a dependence relation, you could just say W minus 2V is 0. All right, let's look at linearly independent sets. In M22, these 4 matrices are linearly independent, and I've given a proof here. It's super simple. And in Pn, which is the set of polynomials of degree less than or equal to n, this set of n plus 1 vectors is linearly independent, and I've given a proof at the end. It's a little tougher. It uses the fundamental theorem of algebra, but essentially what you have to do is show if you have C0 plus C1t plus ... Cn t to the n, and that equals 0 for all t, then all your c's are 0. C0 equals C1 ... equals Cn equals 0. All right, now we're ready for a basis definition. A set of vectors in a vector space forms a basis if the set spans the vector space, meaning every vector in that vector space can be written as a linear combination of the vectors in B, and B is linearly independent, meaning there's no redundant vectors. Let's look at some standard bases. All right, the standard basis, which I just abbreviate as SB, for Pn is the n plus 1. I'm stressing n plus 1 because when we talk about dimension, that number will be important. N plus 1 polynomials 1t through tn. In M22, these 4 matrices form a basis for M22. And this generalizes. So for example, in M33, the standard basis has 9 vectors, and they look like 3 by 3 matrices with 1 in one spot and all zeros in the other spots. In Rn, the vectors E1 through En, those are n vectors, form the standard basis. Now, just remind you, if you're in R2, then E1 would be 1, 0. But if you're in R3, then E1 would be 1, 0, 0. So even though they share the same name, it really depends on what space you're in. Okay, let's find a basis for the set of vectors in the plane x1 minus x2 plus x3 equals 0. The way we're going to do that is, first of all, we're going to take that linear system of one equation and write it in matrix form. And so what we really want to do is find a basis for null A, and A is the coefficient matrix. So what we do is we take A and we augment it with 0 and reduce. 1, negative 1, 1, ... 0. Okay, it's already reduced. So we can just go ahead and write down what a solution set looks like. We're going to start with the bottom with x3. x3 is free. We'll call that T. x2 is free. We'll call that S. And x1 would be S minus T. So our solutions look like S, and the coefficients of the S vector are 1, 1, 0, plus T, and the coefficients of the T vector are negative 1, 0, 1. All right, these two vectors span the solution set, and we saw in the last lecture that automatically those two vectors are also linearly independent. So a basis for null A is squiggly brackets. Bases always go in squiggly brackets because they're sets. And then we just want those two vectors, 1, 1, 0, and then comma, negative 1, 0, 1. Leave the S and the T off. Just those two vectors form a basis for null A. Okay, let's look at theorem 5, the spanning set theorem. We've got a set of vectors in a vector space, and we're going to let H be the span of those vectors. Statement 1 says, if any one of those vectors, I just said V1, for instance, is a linear combination of the others, you can toss it out, and H is still going to be the span of the remaining vectors. And statement 2 says you can keep doing that, tossing out vectors, until you get a basis for H. So some subset of those vectors will form a basis for H. So a basis is the smallest set that will span. If you toss out any more vectors, you won't span the space, but it's the largest set that is linearly independent. If you added any more vectors, you would have a dependent set. So let's look at another example. By inspection, write one of the vectors as a linear combination of the others. Okay, so it's pretty easy here. We can just see that P3 is P1 plus P2. So P3 is actually not needed. It's a linear combination of P1 and P2. So if we want, and looking down at statement B here, if we want a basis for the span of P1, P2, P3, P3 is not needed. A basis would be P1, comma, P2. How do I know those are linearly independent? Well, I look at P1 and P2 and I see P1 is not a multiple of P2. And for a set of two vectors, if one's not a multiple of the other, then they're linearly independent. So those are two linearly independent vectors. So there's my basis. Okay, we're almost ready to accomplish our goal, but first we need to do a short pivot review for m by n matrices. The columns of a matrix A are linearly independent if and only if A has a pivot in every column. That's because you want no free variables in the equation AX equals 0. The columns span Rm if and only if you have a pivot in every row. That's because you don't want to end up with a row like 0, 0, dot, 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 augmented with something non-zero in the augmented matrix. All right, so let's look at an example. Take a look at these four vectors. We want to know if these four vectors span R3, if they're linearly independent, and if they form a basis for R3. So let's let A be the matrix whose columns are these vectors. And I did that in the solution. Here's A, and I reduced A to echelon form. There's no need to go to reduced echelon because I'm just looking at pivots. So do the columns of A span R3? Yes, because we have a pivot in every row. Are the columns of A linearly independent? No, because we don't have a pivot in every column. So do the columns form a basis for R3? No, because the only way that answer could be yes is if the answers to A and B were both yes. So now here's what we're after. How to find a basis for null A and col A. To find a basis for the null space, you just solve AX equals 0 and use the vectors that span the solution. Okay, we already did this on page 2. The example at the top, we went through this process. To find a basis for the column space of A, you're going to reduce A to any echelon form B. You don't have to go to reduced echelon, any echelon form. Then the key part is you're going to use the columns of A that correspond to the pivot columns of B. You can't use the pivot columns of B because row operations change column spaces. So let's look at two examples where I've done most of the computations, so this shouldn't take long. Here I've got a matrix A and its row equivalent to the matrix B. We want to find a basis for null A and a basis for col A. So let's do col A first, that's easiest. So we look at the pivot columns of B, that's 1, 3, and 5. And we use the corresponding columns from A. So basis for col A is squiggly brackets and put in columns 1, 3, and 5 of A. And there's our basis. Now here's what I don't want you to do, and I see this all the time. Students leave off this, basis for. They just write col A equals that set. Well, that's ridiculous. Col A is a space, it's a subspace. It's got infinitely many vectors in it. That set right there has 3 vectors in it. So without the basis for in front, the statement makes no sense. So don't leave that off. Okay, for null A, we're going to imagine augmenting B with a column of zeros on the right because we want to be solving Bx equals 0. So there's actually 5 variables in that linear system. And we're going to start at the bottom with x5. x5 is 0. x4 is free, so we'll call that t. x3 is 7/5 t. x2 is free, we'll call that s. And x1 would be negative 2s minus 4t. Now at this point, you can write out the solution. X bar equals your s vector plus your t vector. Or if you've been doing this for a while, you can jump right to your basis. A basis for null A is the set. You're going to take the 2 vectors that correspond to S and T. So negative 2, 1, 0, 0, 0, comma, negative 4, 0, 7/5, 1, 0. Okay, last one. Null A is a subspace of what space? Find a basis for the null space. Well, A is a 3 by 4, so A maps R4 to R3. So the null space lives in R4. So what space? R4. All right, and to find a basis for the null space, what I did was I took A and I augmented with 0 and I reduced. And so this shouldn't take us very long. We've got 4 variables. Let's start at the bottom. X4 is 0. X3 is t, x2 is s, x1 is negative s minus t. So a basis for null A is equal to the set, and I'm just going to do this in my head. I'm going to read off the coefficients of s. That's negative 1, 1, 0, 0. That'll be one vector. And the second vector will be the coefficients of t. Negative 1, 0, 1, 0. Okay, and that is the end of this section.